So I'm really not feeling well, and so I'm just going to give a very short lecture. And I'll just tell you a few things that are, a few things about lattice, about gauge theory, non-event gauge theory, and about lattice field theory, and about lattice gauge theory. And because I'm sick, I haven't really necessarily controlled all the factors of 2 and I and minus 1. Let's remember that we'll be talking about a compact group with generators TA, and I'm assuming that these generators are traceless, which means that in particular there's no U1, and so the group is simple or semi-simple. These, since it's compact, these are just, the commutators are just linear combinations of the generators, and we define a covariant derivative as an ordinary derivative plus an AI, and I'm going to write that as DI plus I, a coupling constant, AIB TB. Because the group is compact, it doesn't matter whether the group indices are up or down. If you want a candy, just take it from the box. I'm afraid if I touch it, you may get sick. The Faraday matrix, as you know, is a commutator of DI with DJ, commutator of 2 covariant derivatives. And so this is DI AJ minus DJ AI plus the commutator of 2 gauge fields. And in particular, if you write down what these elements are, then this is equal to IG TB CD times DI ABJ minus DJ ABI minus GFB FE. I was running out of letters. AIF AJE. Which we can write as IG TB CD FB IJ. And maybe I should, well, we already have that. This, maybe I'll add just another bit to this. This is DIAJ minus DJAI plus, and now if we have this commutator here, we have AI, AJ, and if we call them, let us say, F and E, we have a commutator here of TF with TE. And so this is DIAJ minus DJAI plus IF. Actually, I left something out here. If there's a G here, then we have here minus G squared.
Can we incorporate G into a tensor? In that case, we don't need to write G.
What's that?
Can we incorporate G into the A tensor? In that case, we don't need to write.
don't quite understand what you're saying. This would be minus g squared plus I f f e l t l actually. I don't know. I might have made a mistake. Anyway, I'm pretty sick. Let's see. There's an extra I and a G, as we have minus G squared, we have that. Then T F T E is I F E L T L. And so one of these equations is wrong. Or maybe the equation is wrong, I haven't written down yet. So let's just, I'll leave it to you to straighten out the I's and the minus signs.
Okay.
The action density is minus a quarter F-E-I-J, F-I-J-B. And this thing is 1 over 4k g squared times the trace of Fij, Fij. So where k is this constant, k delta AB is the trace of TA with TB. So that's that k. And right, the trace over 4kg squared is the LF. Okay, anyway, what I wanted to just, as I said, I'm not going to talk very long today. This is under gauge transformation, the gauge fields do this. And here G is unitary. And consequently, 0 is a derivative, any derivative of GG inverse, and so you get that 0 is DI G inverse plus G DI G inverse. Anyway, what I want to say is that there's something that's interesting, namely an integral, a path integral of the connection, a line integral of it from some initial point to some final point. And under a gauge transform, this is called a Wilson line, and under a gauge transformation, this turns into G of x initial times the path integral. Oh, when I say path integral, I mean integral, path ordered integral. This isn't a path integral in the Feynman sense. This is just a path ordered integral, because these are matrices, and so the exponential of a times a little bit of dx that's near xi goes to the left, and the exponential of ai dxi that's when x is near the final position, that goes to the right. So it's a path ordered exponential times g inverse of x final. That means that if you take the trace of the path-ordered integral of something that is a loop. Then this is gauge invariant. So prime is equal to trace of path-ordered e to the integral ai of x dxi. So this is the Wilson loop. And so what you see is that it's an interesting quantity because it's gauge invariant. And what one does then, as in lattice gauge theory, is to make use of a non-abelian generalization of Stokes's theorem, according to which essentially an integral of ai dxi is an integral of fij dxi dxj over the area that's bounded by this loop. And and then if you're talking about a traceless, a group where the generators are traceless, and you consider something like e to an integral of this ai dxi, and you take the trace, then this turns out to be proportional to fij, say bb, traced. So in other words, this is proportional to the Euclidean action. And so, so the Wilson's idea for lattice gauge theory was to divide space-time into hypercubes and then put a group element, a Wilson line, on each edge. And so that means you have a group element on each edge. And if you take then a path-ordered product around a loop, around a tiny square, and then take the trace, you get something proportional to the action. And that's in the limit, though, in which the size of the tiny square or plaquette goes to 0. I've always been bothered by this for various reasons, but I don't think I'm going to explain them today. So I think maybe we could quit now. Do you have a question?
No. Maybe next time.
Okay.